All right. So we finish IR thermography in this particular class. So if you recall that we state that the received radiation power from a black body of source temperature, it actually scales linearly with the response of the camera itself. So now we can write three collected radiation power terms. So one is emission from the object, which is epsilon tau WOBG, where epsilon is the emittance of the object and tau is the transmittance of the atmosphere. The object temperature is T object. All right. So why they are multiplied by these two terms? If you look at the the previous drawing, you can see that this is the radiation that it receives because it passes through the atmosphere. As it passes through the atmosphere, a part of it is absorbed, part of it is reflected, and a part of it is actually transmitted. So that is the part that we are calculating. Okay? That is what the camera receives, the part that is actually transmitted. All right. All right. So then, of course, there is reflected emission from ambient sources. Okay. So whatever is reflected, a part of it, which is not emitted, so that is the part that is reflected. So that when it passes through the atmosphere, okay, is given by this. So therefore, 1 minus epsilon is a reflectance of the object. The ambient sources can have a temperature of T reflection. Okay. Now, the emission from the atmosphere itself matters. So 1 minus tau is the emittance of the atmosphere. The atmosphere temperature, let's say, is T atmosphere. So you can see that all these things now are taken into considerations. You can see them all here. Okay. So, this is the T reflectance temperature, okay, of 1, which is basically the ambient or the surroundings. Okay, so atmosphere has got a T atmosphere. So this has got a T object. So there are three temperatures, three types of radiation that is impinged on the camera surface. Okay, right. So the total received radiation power now can be written as a sum total of three terms. One term is definitely from the object. The other one is coming from the reflected emission from the ambient sources. And the last term is coming from the atmosphere itself. Remember, 1 minus tau is the emittance of the atmosphere, and a part of that emittance actually is transmitted through the atmosphere, and that is what actually reaches here. Okay, so this is the total received radiation power that you see that the camera gets to see. Okay, that is incident on the camera. Okay, so we can multiply each term by the constant C of the equation and replace the term CW products by the corresponding U. So when you do that, okay, so C multiplied by W gives rise to a camera response, right, or a signal. So the first term that you see is epsilon tau U object. The second term is 1 minus epsilon tau U reflection. Then the third term is 1 minus tau U atmosphere. Okay, so we are interested in the U object basically. So you take this U object out, then you divide everything and you rearrange the terms basically. So what it gives is U total divided by epsilon into tau minus 1 minus epsilon by epsilon into U reflectance minus 1 minus tau divided by epsilon tau into U atmosphere. So this is the total formula that you get. Remember, the only caveat was that we assumed a linear response. We assumed that there is a linear response of the camera, right? And we are interested in the U object. This part is the one that we are most concerned with. Okay, the rest of the things, U total and all these things, okay, somehow you have to account for this. So this is the general formula used in all thermographic equipment. So the voltages of the formula is U object. U object is a calculated camera output voltage for a black body of temperature T object, that is a voltage that can be directly converted into the requested object temperature. U total is the measured camera output voltage for the actual case. U reflectance is the theoretical camera output voltage for a black body of temperature T REFL reflectance according to the calibration. Okay, and U atmosphere is again the theoretical camera voltage for a black body of a temperature T atmosphere according to calibration. You can see where these things are coming from now. The U object ideally would be the calculated camera output voltage for a black body which is temperature T object. Okay, that is what it is. That is what it should be, because you have taken away the epsilon and the tau terms now. Okay, so it is the actual calculated camera output voltage if it was a black body with a temperature of T object. Okay, that is the voltage. It can be directly converted to the requested object temperature, no issues. Okay. U total is the measured actual camera voltage that you are measuring. All right, because that is the total incident that is falling on the camera. Okay, so this is what you are actually seeing. And the other two, U reflectance, that if these are pre-calibrated, that means for different black body temperatures of T reflectance and other things, if you knew what will be the camera output voltage, then these are provided to you by the manufacturer, for example. So, for example, you are working in an atmospheric temperature of, say, 35 degrees Celsius. Say. Okay, so it comes pre-calibrated what the theoretical camera output voltage will be for this atmosphere, considering that the atmosphere is like a black body. So what they do, they calibrate the camera for different black bodies, okay, and they give you a calibration sheet which you can enter. That means when you say your atmosphere has a temperature of, say, 35 degrees Celsius or 45 degrees Celsius, whatever it is, moment you enter, the software package that comes with it automatically calculates the U atmosphere. Then you also need to give what is the T reflectance or the temperature. Once you give that, it will automatically calculate this as well. Okay? So these two terms are automatically inbuilt into the software, because when the vendor sends you the camera, he uses this camera and pre-calibrates it. That means he puts it in for different black bodies of different temperatures. Okay, and he calculates what will be the corresponding theoretical camera output voltage. Okay. Once that is done, it will give you a sheet which you can use now. All right. So this is how it actually kind of works. Okay. So you understand that. So each of these terms, but this U total is the actual camera voltage that you are measuring. Okay. So this is, for example, a case where we this is from our lab, so where we measured the temperature of a polymer droplet, which was at around 900 Kelvin. So this is the droplet, this is how it anchored. So this droplet is actually heated with a laser so that its surface temperature actually goes on increasing. Then you use an infrared camera. Okay, this is the camera that is shown in the previous slides. We monitored this particular droplet and try to measure how the surface temperature looks like. Okay, so the laser that is used to heat the droplet is also an infrared laser. It is about 10.6 micrometer with a 300 watt power, and there is an acoustic levitator in which it is suspended, and the droplet is suspended in an acoustic levitator so that it is kind of contact free. And you use a high-speed camera with a zoom lens to parallelly capture that how the size of the droplet is actually reducing. So the IR camera is used to measure the surface temperature. Now, why the high-speed camera is used to measure the decreasing, the regressing? Because this can go to much higher frame rate compared to the IR camera. So IR camera is not essentially locked with the high-speed camera. Okay, so it cannot take images as fast as a high-speed camera does. All right, but from an IR camera also you can measure the droplet size, so to say. So this is one sample IR thermography setup that we have. Okay? And this is what you see, that if the, well, forget about that, what is a cerium nitrate droplet? It's a droplet which has got a certain composition variation, for example. So this was with 10% laser power. As you see that is go on in the time axis. So, so the droplet, as you know, slowly gets heated and finally reaches to what we call a wet bulb kind of a limit. So you can see that initially you have variations of the surface temperatures. Slowly and steadily, the temperature kind of equilibrates and the droplet shows something like a red, which is about 60 degree or around 58 degrees Celsius. If you go to a slightly higher laser power, now you see a little bit of asymmetry, because remember, this is actually asymmetric heating. So this side of the droplet, because it's a radiative energy source, as we said, part of it is absorbed. So if you consider a droplet, the outer, it's like an onion. So outer layers, as the radiation gets absorbed as it moves in. So that's the reason you have this asymmetry in the droplet temperature distribution. That 30% laser power, you see that there is a significant, difference, an asymmetry, initial asymmetry, but finally the temperature becomes, equilibrated, because, slowly the motion within the of the fluid inside the droplet actually takes care of this. Okay. And this is, for example, the laser-induced evaporation of a polymer droplet. Now, this is polymer PEO concentration. Forget about the nomenclatures. This is once again done at different times. So this is time t equal to 0, and this is a low temperature heating. It uses only 20% of the laser power. That means the amount of heat that you are dumping is actually quite low. So you can see once again there is an asymmetric heating. Now there is a compositional change also within the droplet, and then it slowly becomes equilibrated, and then it starts to shrink in size, and the temperature goes as high as about 80 degrees Celsius. Now, if you increase the laser power, the droplet actually, because of this asymmetric heating, actually deforms. So you can see that there is very strong temperature differential between the two sides of the droplet. Okay, and this is very illuminating, and the droplet bulges like this, and slowly, and however, it kind of never equilibrates completely. The temperature goes very high at around 110 degree 100 degrees Celsius or so, and there is a temperature differential of something right about 8 or 9 degrees, even within a droplet which is very small in size. Remember, these droplets are sub-millimeter droplets to begin with, but this is illuminating that you can capture this level of detailing, okay, from using an IR camera, when there is an asymmetric heating of the droplet. So this is rather good. I mean, this kind of shows that the system is actually very powerful. It can actually do all this, extremely nice, measurements, even for very small droplet sizes. These are sub-millimeter droplets, for example. Okay. You can also do IR thermography in pinned tube heat exchangers as well. So here, what happens is that, this is a very pretty extravagant setup, but but if you look at the test section, which is 5 right around here, okay, so this is where you want to measure the local heat transfer by using IR thermography, and this is exactly where it's done. So it is not just for small. What idea of showing this slide, what I showed for droplets was very small, and this is obviously pretty large. So this is like almost like a bellow. So it is like a at the full heat exchanger assembly. So it is highly versatile, and therefore it can do measurements in pinned tube heat exchangers as well. So like it can measure for these small droplets, and it can measure the asymmetry. It can measure for these kind of large scale setups. Okay. This is the IR thermography on this pinned tube heat exchangers. As you can see, you can readily see the wakes also. So this is like the temperature distribution. This is not the fluid flow distribution, but if you think that there is a certain analogy between the two, okay, so you can see that you can see how the heat transfer, which is basically carried by the flow, essentially. So how it actually varies from different pins. So these are the different pins, and how it varies with the different pins. So as you can see, so this is somebody else's data. So it is, this is the best images that I could flush out. It's from source 8. So you can see that in the aft, there is a high temperature, then it slowly decreases, then it again becomes high, then it slowly decreases. So there is a certain amount of asymmetry, which comes due to the flow asymmetry predominantly. So you were able to capture this kind of details, which is not possible with a thermocouple. For example, if you stick in a thermocouple here, you will disturb the flow. And at the same time, whatever temperature you will get, maybe just this red or just this yellow, but you will not get the field. This field is vitally important because it tells you, now if you plot the streamlines on the top of it, then you will get a very good idea that how the fluid transport and the heat transport are actually happening in conjunction with each other. You can also find out what is the heat transfer coefficient for this pinned heat exchangers, which is what you need for practical applications. So you can also do this, film cooling effectiveness. So what is film cooling effectiveness is that you have a low speed wind tunnel, you have a film cooling article, and then you basically you have the coolant flow through that, and you use an IR camera to see that how the heat transfer is happening with the coolant flow. So how efficient is the coolant flow? That is what is measured. This is from source 9. Once again, this is a film measurement. So we have shown droplet, we have shown pinned fins. We are also now showing that if you do it in a low speed wind tunnel, the film thickness is actually very important. Okay, and this is what the corresponding results look like. So if these are the holes, these are the film cooling holes. This is like how the temperature distribution actually looks like for different flow rates. So we can do a very detailed, so this is Nusselt number divided by Reynolds number to the power of 0.5. So this is color coded, but the Nusselt number calculation comes from the temperature and the heat transfer coefficient, therefore. So therefore, this is how this data looks. Amazing clarity. It gives you the field measurement without being constrained about some thermocouple sticking somewhere and making guesses. So this will actually give you the temperature of the top of the film. So that is what you should be able to look at very clearly. Okay. So these are kind of the sources from which different things are taken from. Some are our work, some of the work comes from other people's work, of course. So the work comes from Srinath Ekar from the film cooling effectiveness, and also from the work of Jerna Ya. But there are certain things that we wanted to mention at this particular point. We have come to the close of the lecture, that the IR thermography is therefore based on certain amount of calibration and certain amount of details that you get from the camera signal and how you calibrate it. You also have to key in, this is what I forgot to mention, you also have to key in this epsilon and tau. These are parameters that you need to put in. Atmosphere is normally pre-calibrated, so these things are already there unless you want to do in a different atmosphere, but normal atmosphere conditions are given. Epsilon is something that you have to enter. So when you operate an IR camera, you have to enter that this IR camera has got, this object has got an emissivity or emissivity of whatever. So that is something that you need to know. Because if you do not know that thing, then you will have an error in your temperature measurement, because you can see it is very sensitive. These things are all pre-calibrated and entered with you. So, and this is also, that what is the black body temperature going to be. So it is kind of, once you know all these parameters, okay, these are all pre-calibrated. This is something that from your actual measurement. This epsilon is something that you are entering. Tau is already pre-existent. So when you do all these things, you know your U object. Moment you know your U object, from the calibration curve, you know your T object. Now, this can be done from pixel to pixel, because of the simple reason is that, IR cameras, you can do pixel to pixel, because if your object has got a surface varying temperature. And that is exactly what we captured here, for example, surface varying temperature, right? Or in the later part, this surface varying temperature. So naturally, that is the USP of doing this. So at each point, it can actually do this. So it is pretty sensitive in that particular way. So at each pixel resolution, it can do this. But also at the same time, because it actually registers a certain amount of radiation, the pixel resolution is not all that great compared to the normal CMOS cameras that you use for high-speed imaging. And also the frame rate cannot be as high as IR cameras, high-speed cameras, so to say. So there's a certain amount of calculated risk in always. There is certain amount of error, especially if the ambient is very fluctuating. For example, if it is showing fluctuations, for example, if it's a hot day and it's showing buoyant plumes, so there is a plume that is going on. You can see that in the desert. So there is refractive index variations. So when we do the Schiller, that will be the thing that will be important. So in those cases, when this is time varying quite a bit, okay, and when the atmospheric temperature is not exactly the atmosphere which is fixed at all times, and it is varying, time varying, so that time it poses a little bit of a difficulty, especially if the variation is too fast. For example, if there is a turbulent plume that is in front of your object. In those cases, the accuracy of the measurement actually goes down quite a bit. So you have to be careful. All we are saying is that when you utilize these methods, you have to be very careful. Surface curvature effects also comes into the picture, because not all radiations come, and that you cannot be able to collect all the radiations uniformly. So that is one other point of concern for this. But if you do, your IR cameras are manufactured in such a way that some of them are pre-calibrated. The normal setting where there is not a turbulent plume, if you want to measure the surface temperature of something, okay, you should be able to do that. But you cannot do it, for example, in a highly fluctuating environment, like in a turbulent flow, for example, or a turbulent flame, because it is just simply not possible. It's simply too onerous to calculate the temperature in those kind of systems. So you have to utilize film cooling, pinned heat exchanger, droplets, surface temperatures in applications like batteries or thermal management tools. In those cases, I think this will be highly, highly useful, but it would not be useful in all the cases. That is what the whole point is. So whenever there is turbulence and other type of things, these simple methods that we kind of talked about here may not be all that applicable. But you understand that it all depends on the black body radiation, how you collect the radiation, and what are the contributors to this radiation. And we also gave you a little bit of a primer on black body, non-black body, Wiens displacement law, the Planck's constants, and stuff like that. So these are kind of, and we also talked about the IR thermography spectrum and the electromagnetic spectrum, and we said that why around these temperatures, IR is actually quite useful because it peaks at that particular wavelength. It peaks in the dark, actually, so to speak. So, but the signal becomes weak, as we know. So as the temperature goes down. So that is also a problem, but it still has got a very wide variety of applications, so to say. It has got many things that it can do. It is highly effective, as these kind of images actually show. So it can give unprecedented resolution on the heat transfer calculation. Okay. So further readings are suggested. So you can read a few research papers. These are all research papers. Okay, you can also look at Alden's lectures on molecular spectroscopy. That is for absorption spectroscopy as well as for IR thermography to a certain extent. Okay, and once you do all those things, you should have a very good idea that what type of things we are actually dealing with. So the methodology, it is a last I want to mention before we end this lecture is that it's a non-intrusive method. Therefore, we don't need anything to poke the flow or poke the system with. Your thermocouples and other things, are point measurements, so they will not pick up any spatial variations. It might pick up the temporal part, but not the spatial part. IR thermography, obviously, if you have a very rapidly varying temperature, it cannot measure that to that high FPS. It has got reasonable resolution, but not very high resolution. so that you cannot resolve at the same level as your normal CMOS 4K cameras does, for example. So there are certain limitations, but still it's a field measurement, and because it's a field measurement, it has got a lot of utility uh, in the community. So I think we should end our lecture here. And so IR thermography is something that is there to stay, and you can read more research papers. You can look into more camera details. FLIR is one company that manufactures IR cameras quite regularly. So you should look at those. And there are also an IR camera has got different ways. It has got bolometer based techniques and other things which we are not covering in this particular series of lectures. It is more on the fundamentals and how it is measured. Okay. So time permitting, we will also provide a little bit of a small video snippet which will show you that what kind of IR cameras actually exist, what technology. That means the hardware part of the IR camera, that how do they sense the signal, how do they respond to a certain amount of radiation. Okay, so we would see you in the next class.